see if we're on. I didn't hear it. Okay, for Chapter 1, the science of chemistry. What is chemistry? Chemistry is the study of the composition, structure, and properties of matter. And the changes in composition, structure, and properties that matter undergoes. Now, and the central objective in chemistry, of course, is the study of matter. What is matter? Matter, by definition, three stripes is by definition, anything having mass and occupying space. So what does that entail? Everything. So what the issue is, we need a better way of studying everything in the context of, studying matter. In the study of matter, there are three issues that are of critical importance that kind of go together back and forth. We see the composition. That is, of course, what it is made of. And then we'll be talking about structure. How does it go together? How do the different parts of the material go together? The organization of matter, and properties. Well, it is the properties that define what the chemical does. And chemicals are not just two-dimensional drawings on a chalkboard. They are living creatures, so to speak, that come alive when the presence of other living creatures called chemicals. And these are properties. Chemical and physical. Now, if we're talking about chemical changes and chemical properties, these are reactive properties that produce new materials. Now, of course, matter is neither created nor destroyed. It's just changed in form, and that's what I'm talking about, changing in the form. But physical properties only change in dimension. They don't change the chemistry or the internal composition. So we can break a length of chalk in half. Well, we still have chalk in both halves. And so really the chemistry hasn't changed. water can transition from liquid into vapor, and one's liquid, one's gas, but both of them are still water. So that's what I'm talking about in the nature and definition of properties. Okay? So when we talk about the study of matter in chemistry, we need to break it down into something that's more basic and easier to digest, so to speak, and allow us to look at the details and then build back up to the more complex. So there is a flow chart that I use, and its context is matter is simply divided into two major categories, mixtures and substances. Now those two terms are very important in the language of chemistry and how we discuss things. When we talk about mixtures, these are physically prepared and physically separated. There's really no no changes in the chemistry of the components of a mixture. Mixtures are physical in nature. And we find those the most visible ones, of course, the solutions. And solutions are, in general, a homogeneous mixture. Now, mixtures are also divided into hetero. If we're talking about homogeneous, this is consistent properties throughout. Whereas if we're talking about a heterogeneous, is inconsistent properties throughout. So this is not too difficult to comprehend in terms of, say, a homogeneous mixture is like an example of dissolving sugar in water. So everybody could take a spoon of sugar and pour it into a glass of water and stir it, and eventually the solid would disappear and take on the same state of existence as the solvent in which you dissolve the sugar, right? I mean, that's kind of an obvious conclusion. Well, if you sampled the mixture and tested with your magic tester, you'd find the composition would be the same anywhere you test it. However, if you are working with heterogeneous and inconsistent, something like a sulfur, which is a bright yellow powder, plus charcoal, black powder, it would be easy to see the speckles of yellow against the black that's inside that mixture. And if you sampled it, what you would find is a variation in percent composition. And so when we talk about one category of matter, we talk about mixtures in the context of either homogeneous or heterogeneous. And the other category of matter is, of course, over in the context of substances. And these are chemical in nature. So when we classify matter in terms of substances, we're talking about something that is described in terms of its chemical nature. And when we describe a substance in its chemical nature, all substances, this is a biggie, all substances are simply homogeneous. They have consistent properties throughout. But the issue here in substances is that they are divided into two major categories: elements and compounds. Terms that we are very familiar with in a generic way. We know about the periodic table of the elements. You've seen them in other courses and in your lifetime. And you know about compounds, which are these weird-looking things that people like me draw on chalkboards all the time. And they make up the composition of who you are and everything else that we are associated with. But both, when we discuss them, are homogeneous matter or materials in the context. Now, to distinguish between these, we want to give specific definitions. So when we talk about elements, what are elements? These are elements are the smallest entity of matter with specific chemical and physical properties. And cannot be broken down by ordinary chemical or physical means. Requires a nuclear reaction to change an element. Compounds, you'll find, have the same essential definition, except at the end of the verbiage of that definition, these can, instead of cannot, be broken down. These compounds can be broken down into two or more parts. So that's essentially the difference in the two definitions. So compounds are the smallest entity of matter that can be broken down into two or more parts by physical or chemical means. When we talk about ordinary chemical and physical means, what are we talking about? We're talking about heat, light, or electricity. So if You take a substance, you heat it enough, you might break it down into components. It'll degrade a lot of stuff. You can set a piece of paper on fire and it changes its composition. That's breaking down the substance into something different, into maybe smaller components. Light will degrade some things, electromagnetic radiation. Electricity going through is frequently used in refining to take a salt and break it down into simpler forms. At any rate. Or the theory of material world. Now, the first atomic theory was presented from a philosophical standpoint, 600 BC, that Democritus has said if you take a piece of matter and divide it in half, and then half of that half, divide it in half, and then take each of the halves infinitely and keep breaking them down, you'll come to a particle which is indivisible. And in Greek, that's called atomos particle. That's the source of the word atom. And in the philosophical standpoint, when the models of the atom were first being studied, it was believed that the nucleus was indivisible, could not be broken down, and hence it evolved, and the name of the nucleus, or the structure that contained the nucleus and electron clouds, as it was known then, early 19th century, 20th century, was the atomos particle, or the atomic structure. But what Dalton came up with was the first classification and organization of matter based on the scientific method. In which he said that all matter is made up of atoms and elements. Oh, I know what I wanted to tell you this. This is kind of a little sidebar, but it's important that you understand the semantics of what I'm talking about. The terminology that we're using is elements and compounds right now. But let me explain what the elements is the same thing as an atom. Okay? An atom is an individual entity or particle. But an element is a large number. They both mean the same thing, guys. I think you can appreciate that. But in the semantics of discussion, when we say an element, we're talking about a whole lot of these atoms of a certain kind. And in same way with compounds. And from a semantic standpoint, this is the same thing as saying molecule. This is an individual or single entity. And compounds is a large number of particles, of molecules. So what I'm just giving you a kind of a perspective on the semantics of who's who in the world of molecules and elements, compounds, and molecules. Anyway, going back to Dalton's atomic theory, he said that all matter starts with the simplest structure, and the simplest structure is the atom. Now we know today that the atom is composed of atomic structures like the nucleus, and protons and neutrons, neutrons, and electrons, and even smaller particles even beyond that. But those are fundamental particles. Well, we're going to start with the atom to begin with, anyway. And so when we talk about the atom, we start using then all atoms of the same structure are the same chemical and physical properties, and those that are different have different chemical and physical properties. But anyway, atoms produce elements. Okay? So periodic chart, and we'll show you how to distinguish between the various elements and what they are, the metals and non-metals, the metalloids, and then the alkali metal, just a whole lot of stuff. Atoms, elements, and then what happens with atoms and elements when they interact, they make molecules. And a whole lot of molecules give compounds. And then compounds interact with elements and other compounds through chemical reactions. And then chemical reactions produce only three things. Do you know that? Under normal, ordinary conditions, less than 5,000 degrees, only three things can be produced. That's a solid, liquid, QUID, or a gas. That's it. Now, we can take those and mix them together, and what do you get out of this? Solutions. Now, that is your course. That's how the traditional course in chemistry is put together. You start with the simplest structure. We took matter and broke it down into mixtures and substances were broken down into elements and compounds. And the elements are essentially atoms and what have you in the periodic table, and compounds are two or more of the elements hooked together in certain ways, chemical bonding, and making certain substances with their own chemical and physical. So if we start with an atom, and it's the simplest particle that we can work with, and learn about it, then we can learn how to hook other atoms to it, and then make it more and more complex until we go through this sequence. And that's where your course is laid out in the study of chemistry that we're going to go through. So when I start, say, in the next chapter, the beginning of the next chapter is atomic structure. How do you look at the periodic table and take the data out of one of those little blocks and say, well, how many protons, neutrons, electrons does this substance have? Or this atom or element have? And that's what we were talking about, starting with something simple and building to the more complex. We'll classify compounds and molecules. And compounds are divided into two major classes and break them all down and show you how they come together and what have you. And then we'll talk about chemical reactions. Now that's the essential study of chemistry in some people's eyes and mind. Chemical reactions is the course. Now that'll be almost the entire course in Chem 2. Chem 2 is the study of chemical reactions and so how do we study chemical reactions? And anyway, I'm not going to get into that, I promise. And you have at the end of this semester, when we get to chapter 11, states of matter. And many of you have already heard that expression, states of matter are solids, liquids, and gases. And they have solids have properties, and liquid phase has properties, and gas phase has properties, and the transitions between those phases have certain characteristics that we are going to learn about. And that's what we're talking about. But we first have to start with something simple, like the atom and the nucleus, and what are the models of the atom and so forth, and then build it up to the more complex reactions that produce these solids, liquids, and of course there are millions of solids and millions of liquids and gas phase particles. And then when you mix a solid into a liquid, sugar into water, you get a solution, or gas and liquids. So those is what we're talking about. Talking about starting with something simple and building to the more complex. Because we're going to add pieces and parts as we go through the course. Because you're not ready to jump into solutions right now and understand the properties and mechanisms that govern the characteristics of solutions until we understand what goes into those solutions from a simpler point of view. Okay. Now, this is something that most of you have probably covered many times in science courses as you've evolved over your education. And it hasn't changed, and hopefully it won't change between now and then. Now, we're going to add to it. But in applying the scientific method, it is very important that you, as a young scientist, develop an appreciation of the steps that are associated with the scientific method, and to learn how to focus your attention into the problem of solving the concepts and understanding those concepts which are in the science of chemistry. And so there's a systematic way to do that, and it again is called the scientific method. Now there is two sides to this story. One is a listing, pragmatic set of steps. Do this, 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 and this, and you come out with an answer. Okay, that's fine. That happens and that works. But there's another side to it, which is an intrinsic side, which you have to develop a kind of an intuitive feel for studying the material. I tell people that in studying the scientific method here and studying chemistry, it's like driving a car in a fog, and you keep studying it, and you keep studying, you keep working on it, and at some point in time, that fog will clear. And when I say there's another level of learning, that's what I'm talking about. You study until that fog clears. You see the big picture. When I say you study till see the big picture, that's best advice I can give any of you at any level, on any subject. You dig in and you outline and you condense and you make it a part of you. That's one thing that you need to understand about the study of anything. You need to take the material, new material, especially like you're listening to me give you definitions and stuff. How can you turn that information that you've got into something that fits you, your personality, your psyche, your nature? Until you do that, you're not going to learn anything. You have to make it part of you. I sit up here and I just rattle this stuff off like it's, yesterday's lunch menu, because it's part of me. I've made it part of me. I've taken the time to whittle it down to something that, the epiphany, I see where the light is now, and how to do this type of material. And that's a philosophical point of view, but it is very important. You have to kind of sit back and say, I'm going to take the data and the facts and say, well, what am I looking at? And we're going to do this. I've got a little mind experiment that we will do in a few minutes that will take you into this study of chemistry in a way you've not done it before. Now, we'll set it up in a minute. We'll take a break in about 10 minutes. Okay. The standard, if you will, scientific method is one. Identify a problem. You need to know where you're going. If you don't know where you're going, you're just going to be wandering in the dark. So the problem that you are going to study, I call, and I like to call it, and it makes sense this way, object of interest. That's just about anything, right? Obviously, it's why are you studying chemistry? What are you studying in chemistry? What is this? That's the object of interest. Rhetorical question. And so you get into this and you look at it, and so I have to focus my attention on that issue. That's what we're talking about. You're learning about the scientific method right now. That's your object of interest. Well, how do I apply the scientific method? I have to get a strong handle on what this problem is. Why is the wall blue? Why do you perceive blue? Why do you hear what I'm saying? Those are objects of interest. Why do suns shine? Object of interest. Why do plants grow? Object of interest. What does this chemical do? Object of interest. That's the point. It is what is the subject of your study? What is the interest here that will stimulate you to ask questions? So you're interested. What's the next step? Then you want to collect information on object of interest. Very time-consuming aspect of it. So you're looking at a blue wall or sound. Where would you go? Well, first thing I think of is the library. Okay? But there are other aspects and other places to look for clues and secrets of the universe. So what is thinking outside the box. Adding information. This is your collection of information. Information overload. The more information you can put together, it may not make any sense and it may not be correlatable as you go through it. But at some point, the fog will clear and you will begin to see the big picture. Study to the big picture. Study to the big picture. You'll hear me say that often. At some point in time, while you're collecting information and reading about this interesting object that's just consumed your nature, you're going to come up with an epiphany. Oh yeah, I see what I'm looking for now. That's called the hypothesis. You form hypothesis. Another definition of that is an educated guess as how to solve problems. So with information that's rattling around in your brain, you start correlating these factoids that you've heard about. And you say, I can put A, B, and C together and I can get D. From a theoretical standpoint, you've got this mapped out. But keep in mind, yes, this is theoretical. It's different from the practical. Practical means you have really proven yourself, and that's the next step. Experimental. The experiment. What's the purpose of an experiment? Is to verify your hypothesis. Or prove your hypothesis. Okay, a titration. You want to find the concentration of acid in a solution using a base. So you collect the data, and you see how to do it, and then you go to the lab, you set up the equipment, you will do this, and you will do whatever needs to be done, and you come up with a number. Now, the experimental process is a very time-consuming. It takes years sometimes to verify hypotheses. And some hypotheses, you have to wait for the right combination of the universe and the right time in the universe to reach whatever to experiment. And so it's a real frustrating world out there in terms of experimental science. But this is the practical. That's a C. Practical science. This is the real world interaction. Up here, theoretical world interaction, you can do anything. This is Alice in Wonderland in part 3. But experimental is the real world. This is a rocket on the rocket pad. Is it going to work? And if it goes boom, dud, that it didn't work. But that's the next step. And so after all of the experimental analysis, you have conclusions. Conclusions can be, of course, you've heard, divided into two major issues, laws and theories. Now, laws are irrefutable, incontrovertible truths. law of gravity. There is always an interaction, and nobody's been able to prove otherwise. When two bodies come within certain proximity to one another, some mysterious interaction occurs called gravity. And we're sitting in your chairs because of that. Okay, so those are truths that I think we all agree. If I release my pen above the floor or above the thing, I think we all agree that it would move toward and fall. Okay, these are irrefutable truths. But when we get into theories, these are conclusions or experimental observations that fit the facts of the system. That's kind of hard, that's kind of abstract right there. Theories are truths that can be modified. That's the way I like to look at it. Now, there's nothing wrong with a theory. There are three theories of acids and bases, say. The Arrhenius theory, the Bronsted-Lowry theory, and the Lewis theory. No one of the theories is better than the other. It's just a matter of what fits the circumstance that you're looking at. And talking, because they all three are theories, but they're based on different aspects of the acid-base concepts. But they can be modified to describe whatever your object of interest. Now, the conclusion is the epiphany, is the results of your object of interest. Is a real description of object of interest. So what you're trying to do is start out with your object of interest, collect information, come up with a hypothesis, go to experimental and prove that hypothesis and verify that your object of interest and the thing you're studying is what you want it to be, or is what you're seeing, or your observations. So that's kind of a strange way to present it, but it is the scientific method. Okay, if everything works. What happens if it doesn't work? When you go through all this laborious effort and setting up stuff and years of experience, at the end, it didn't work. What do you do? No, you don't commit suicide. No, that's not part of this. Okay, you go back to collect information. It's kind of like a loop in a computer. The best analogy that I found for this is when you work in math problems, what do? You run over to the back of the book and you look and see if you got it right, okay? I know I used to. Well, if I look back there, it ain't right, what do? You go back and you read some more stuff in the book, right? Like that. But anyway, the idea is, what do I do now? Okay, you go back and, well, what did I miss? I always say, I worked this problem before like this, when you say, what did I miss? I was working one online the other night, and it came out just totally off the wall wrong. And I said, no, that's not it. What did I miss? I went back and said, oh yeah. And so that's what you're doing. You go back and you review your information like that. So that's a kind of a thumbnail of the scientific method. Now I'll throw you a question or two on the exam that will kind of give you a scenario. What is an hypothesis, Okay, you've got an educated guess. So you'll throw it very straightforward stuff. Okay, so don't panic in trying to turn this in, because that's a lifetime study right there. But the other side of this coin, and this is where you as a scientist will mature when I give you this next story. And this is what most people are presented with in terms of the scientific method. It is correct. There's nothing wrong with it. And I expect you to apply this. As the world and the community of scientists expect me to apply those principles in this same way. When I do research, it's a very, very simple concept, system and surroundings. Now, to understand this, that's a T table. On the left side we're going to write system. And on the right side, surroundings. Right there. The system is the object of interest. What are you going to study? All right, don't lose me now here. This is where it really becomes together for you. Should come together for you. Now think for a second of what your world is in scientific terms, the physical world that's around you. What kind of objects of interest do we study? Astronomy? Give me an object of interest. What do you study? I've given you mine, astronomy. I love astronomy. What do you like studying? Anything, doesn't it? Scientific now. Yeah, I know. Sometimes it takes a second to untangle the cobwebs. You study biology, Yeah. What in biology have you studied?
What do you mean, like?
Huh?
What do you mean, like plants, animals?
Do what?
What are you meaning?
Just anything in biology. Say something about biology. What topics in biology have you studied before?
Animals.
Okay. How about the animal kingdom? We want to study the animal kingdom. What's an object of interest? Outside, no, don't give me biology again now. Get something outside of that. What have you studied?
Nutritional sciences.
What?
Like the study of nutrition.
Nutrition. Okay. Food science. Okay. On the end down here, ma'am. Number one. Give me an object of interest. What you like to study? Now, all these are big picture topics now. How about something smaller? How about the, when I'm talking smaller, falling balls or cannon fire or something like that. You know, paint on the wall. You paint your room? Have you ever painted a room before?
Yes.
Yeah, okay. What did you do? I mean, did you pick a color?
Yeah.
Okay, how about colors of paint? That's an object of interest, isn't it? That's what I'm trying to get you. I'm trying to get you to go to something that you're familiar with. We want to study paint color, all right? I'm not trying to pick on anybody, please. Don't take this wrong. What I'm trying to do is say, okay, now in each one of these, what can we say? Let's take the paint color thing. What can you say about paint? No, let's pick on somebody. What do you say about paint? I hadn't picked on you yet.
What about it? Like colors?
Okay, we've already, okay, we've got color. What makes color, right? Okay. That's an object of interest. What else in paint?
Brushes.
Brushes. Application. Okay, ma'am. Something else in paint.
Maybe like how thick it is. How like thin or thick the paint is.
Okay, thin, is that what you said? Okay, that's called viscosity in the scientific, texture, okay? Okay, let me see the chart. I'll pick somebody out here. Anthony,
Yes.
Pick something else in paint that might be interesting. Now, don't pick anything on that's already been picked, obviously. Something,
How resistant it is to wear? So like if you would paint it on the outside of your house or on the
okay.
outside of a wall?
Applications, but exterior properties. I'm just throwing things out. Okay, now, we're studying paint. Now, if you looked at color, can you subdivide that into something in color? Let's see. Have I picked on you yet? No, you're Michaela? Okay, what about colors?
The type of pigments.
Pigments. And of course, A type, B type, C types, and stuff like that. And so we're beginning to break things down into different points. So we're starting with something that's complex and breaking it down into something simpler, okay? A texture. Nathan, what does texture mean to you, sir?
Like a coarseness, like a
Smoothness,
like a-
coarseness. So texture, surface characteristics. And with that, we can break it down into different categories, can't we? Yeah, you look at the wall. What kind of texture would you see? See, I'm not asking you to answer that. I'm just saying that when you look at the wall and you see some kind of texture, the terminology, you begin to separate things into a category. Rough, smooth, average. How do you're putting together the idea of what you're looking at. So you're taking a system that you're looking at and you're breaking it down into something that's simpler to study. And then you take that one item and you beat it to death. And it may take you a lifetime to get through from A, B, and C. But do you see what I'm talking about, guys? I'm trying to give you a perspective on you want to study something, try to break it down into simpler components. And once you get to that component, you want to study it, collect the information on it. That's how to evaluate your system. Now, what really makes this thing come together is when you look at that wall, what I'm about to give you is going to be kind of weird. What is that wall saying to you? No, you're not crazy, and neither am I. But what does the wall saying to you? Now, this is rhetorical in this context. That's the secret of scientific applications. Surroundings, these are the system. The wall you're looking at, the color you're looking at, the pigments you're looking at are still in the system. That's the object of interest. But what about you? How do you fit into that? What is your position relative to the wall you're looking at? That's called the surroundings. And the surroundings, by definition, is everything else. So we're looking at textures or pigments in specific. So look at that. We've seen a pigment, blue, texture, average smoothness. Okay? How do you know? The wall said so. Yeah, I'm crazy. Doesn't it? You can't, when I ask you, say, what color is that wall? Blue. Okay, I think it's blue anyway. Am I crazy? Yeah. Okay, it's blue. How do you know? Because I told you? I don't want to be embarrass anybody, but the point is, that wall has to tell you it's blue. And then you go up and you can see the smoothness of it. It's a fairly smooth wall. Doesn't have any big grainy look to it. How do you know it's smooth? Well, it's my experience. I know it's smooth. In that, how do you relate to that? This is the secret that I'm trying to get you to think about. You are part of these surroundings, guys. You are the basic entity. You are an observer. You are a receiver. Your senses, your eyes, ears, nose, throat, feel, receive signals. Object of interest is sending signals to you as an observer. You're the observer. You're the observer. You're the observer. Look at that wall. What does it say? Blue. Isn't that right? Now, the wall says blue, but you as a observer received the signal from that object of interest, didn't you? Where? Eyes. Or what other way would you be able to test color if you closed your eyes? I don't know. I don't think there's one, is there? What color is, that's kind of hard to do. Okay, yeah, really. What about texture? Now I can look at it and get a texture, but if I close my eyes, went up and rubbed it, can I define some kind of texture that way? Sure. You are a receiver, a detector. Yes? Make sense? Now go next door and you look at the wall. You rub your finger on it. I got a texture of that wall, and then I've got a color that my eyes see, and so you write down room 132, and then one. I don't think there used to be a classroom over there, believe it or not. And 131, well, it has a certain different texture. So you have a comparative. That's science. But you're still the receiver in this. You are an instrument collecting data. You are a detector. That's all of science, right here. You're a detector. Now, what's the difference between that and maybe study of stars? Well, you can see the stars, yeah, and you can tell they're far away. You can write down a list of things based on what you have. But what about the unseen? How do you see that? Unseen, how do you see that? Well, stupid question, right? Huh?
With other kinds of detectors? Other kinds of detectors, like telescopes?
Exactly. Other detectors. I want to study what's the energy source of the sun? Now, I think we all have heard that it's fusion and yada, 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 and stuff like that. Well, that's a reaction of what? How do we detect what is reacting in there? Use a detector. It's called a spectroscope. Many of you have heard of spectroscopes. If you haven't, that's all right. It's a detector. The essence of science is to recognize an object of interest, seen or unseen, and create a detector. You create a detector that will receive signals from your object of interest. That's called data, isn't it? And you look at the data. You rub the wall and you see the wall in 132, and you go to the next room, you rub the wall and see the color of that wall in the other room. You write them down. You compare the two. That's data. Do you draw a conclusion? Yeah, I like room 132 more than I like room 131. That's a conclusion. This one is brighter, has more effect on the eyes. This one's louder, this is softer. Sounds, visuals, clouds, weather, everything. You are a detector to start with. And you have limits. So what do you do if you can't see something? You create something that will see it. That's the whole essence of science. In chemical reactions, we have detectors that identify ions and chemicals and compounds. We're interested in the structure of a compound. We stick this chemical in this machine. Out comes this weird pattern, and we look at that pattern and say, "Oh, that's carbon dioxide." Because what you're looking at is the language from the object of interest that's sent into the detector, and you see blue. That's the whole essence of science. You an observer or a detector. And what do? You detect and you draw in data, and that's what you're going to do. You write down the list of things that you see and think about it. Well, what does that mean? That's what I'm trying to teach you about. Object of interest sending signals to you as a detector. Now, your detector may be the spectroscope, but it collects data from that object of interest is what we're trying to teach you. And with that, you draw conclusions, that room versus this room. That's the scientific process. You don't have to have step 1, step 2, step 3. You looked at the big picture. You know the difference between blue and white and red and green, or 1 mile and 1 inch. This is because you as a detector have created those outcomes. Okay. One little statement. Albert Einstein. To understand the secrets of the universe, one must first learn its language. And that's what you're here to do. Learn the language of chemistry and how to hear and understand and translate the signals and semantics of chemistry into a meaningful description of your object of interest. Take 10 minutes.